You go ahead.
Okay. So today we are glad to have Mr. Prashant Kansal, who leads the power system team at Tesla with focus on battery energy storage system, power system model development, grid interconnection, and balance of plant study and IBR grid performance study across the board. Prior to Tesla, he worked at American Electric Power, Schweitzer Engineering Lab, and Engineers India Limited, with experience across NERC, TPL studies, grid studies, protection design studies, freezer application, property, and substation design. He got his bachelor in electrical engineering from Delhi College of Engineering, India, and a master in electrical engineering from Washington State University. So he was our alumni. So today we are really glad to have him to give us a talk. And with that, floor is yours. Yeah, please go ahead and start your presentation, Prashant.
Yeah, thanks, Saeed, and thanks for inviting me for the talk. I mean, it's a pleasure to be presenting at WSU. And yeah, thanks to WSU, like I was telling previously, like I definitely feel that it really helped me accomplish what I wanted to. So, and thanks to Dr. Bose, who was my advisor too. So yeah, I think today I'll focus on the talk is mostly focused on energy systems, and I know there's a lot of talk in the industry about not in the industry, like obviously in the world, like about global warming and cleaner environment as a necessity to move the world forward, so as to say. And I think I think trying to like through this presentation, I'll try to provide a bigger picture of energy systems in general and why they are a must. I mean, they are central to this whole goal of cleaner environment. Um, so yeah, let's get into it. And on the introduction side, I think Said mentioned it all. Basically, I lead the power systems engineering team, which is a global team at Tesla. Um, and our team is responsible to develop all the dynamic models for battery storage system that Tesla produces, make sure they're usable in different software platforms for the grid studies. And we also have our hardware in loop testing, basically services in-house. And I'm very involved, and my team is very involved generally across the world, defining the grid performance requirements, basically what the battery storage system needs to be doing to transition to the grid, to transition grid to 100% renewable. Like, what is it? How should it really perform? So that's what we try to define. Previous to my current role at Tesla, and maybe this is a good background for like the students in the room, is like I worked in various companies and like somewhat consciously, somewhat luckily. So when I started in the industry, I started my first job in a EPC. It's engineering procurement construction firms, more like what you would see like Bechtels of US or Floor of US, basically whose job is to like build anything like airport, refinery, buildings. They're typical EPC company. They do end-to-end engineering, procure the equipment, and construct. So I did that type of work in India, and then I came from a master's in US because of like for my first job, I didn't understand like how things are really designed. So I felt like I should study more. So I came to US, and then luckily SEL was next door, and one of the like just like this talk, someone from the research SEL research was presenting in one of the coursework, and then he asked my professor like if you have a student who can do internship, and that's how I got my internship in SEL, and then started my internship, then full-time job, did research work and also studies work on protection system studies, working with Venkat Mainam, who was my boss there at the time, and a really amazing team, and learned a lot about protection. And then when I was there, I did not understand like what is this NERC about, this national basically North American Electric Reliability Coordinator. What is this work about? I used to like hear these terms, but never understood it myself. So I wanted to try like the utility side of the business, which is the end customer really. And at that end, I could do grid stability studies, do work on synchrophasor application, which I learned in school as my thesis, also at Schweitzer. So kind of did a lot of good work there, which helped AEP a lot. And then also worked on the distribution energy resources impact on transmission, and then power quality issues. And the reason I'm just saying all of this, I'll try to connect it back to especially for the students towards the end. Like I do feel like this was kind of a critical thing that um, helped me at Tesla a lot to go through these transitions. And then when I was at AEP, I was leading this renewable energy task force. And I understood the models, but not really in depth. I did not understand exactly how everything works in the inverter-based realm. So I really wanted to try something in inverter-based resources, and I just got lucky to be at Tesla at that point. And yeah, so that is my background. And I did my bachelor's in India and then master's here, as I said, and Dr. Bose was an advisor. And it's funny, like when I was doing my thesis with Dr. Bose, so I came from India, and then Dr. Bose asked me to work on a smart grid communications requirement, and I asked Dr. Bose, "Hey, I know nothing about communications. That's a thing actually I fear." So, and I feel so lucky actually to work on this thesis because this was a cross-functional thing at the time. Like, how do you map the grid requirement to communications requirement? And it became a widely cited paper, to my surprise. And I know Dr. Bose used to like say this, like this is a critical work. And yeah, but point being, I think some of the things like connecting the dot previously, like it really helped me like to do this work, and really well cited work actually. Okay, so I think with that context, like just keep going. So as I was saying, I think like when you think about power systems, like whatever you're studying in school right now, I feel like this is the fundamental of what is essential for grid transition. Meaning everything, like everything that you hear in context, like today about cleaner environment is essentially at the core level saying like you have to electrify. And the reason electrification helps at a high level is because like you basically like if you think about, I mean there are two sides to it, right? One is once you electrify you can like do a lot of things local. Local meaning like if you have electric car, right? I mean you can charge it at home, because you have electric infra there, you can produce your generation there. Similarly on the grid side, like yeah, you can produce the power from renewables. You can basically store them in a battery and do something about it. So and I'll talk more about this as we go, but so there is an underlying principle to this why electrification is happening at a scale. um and yeah, maybe we'll talk about this more as we go into it. But essentially if you look at the pie chart from left to right, except agriculture, like everything in theory can be electrified. And that's kind of what is happening, be it the grid, be it the industrial load, which is lot has to do with the heating, or be it transportation. And I think all the things you're learning in the school will basically help you be in any of this area. So just to now focus especially on the grid side, um, like there is a lot of change right now, both on the generation side of thing and the distribution side of thing. And this is not like in future, this is happening right now. So like on the renewable side, we are all aware like wind, solar, and battery are replacing the coal mostly. And then there is a lot of renewable farming, there is a lot of markets that are evolving, there are issues around how the grid is transitioning from the synchronous to the inverter based resources, typically blanketed as a grid strength, the kind of word that you hear in the industry, grid strength or inertia. And then, there is a lot of, services around how can you defer the transmission or distribution line build out. So, um, and basically another thing, which is something I did not realize when I graduated from the school, is like the whole grid is planned using models. Um, like be it your transmission or distribution, somebody is studying it behind the scene to grow the grid. So this is a critical one for as a message. I feel that this for the students especially, that anything that you're doing to learn the math of how the linear system works or how the control systems work, or like power flow analysis or stability analysis or protection. The reason it is important is because you will eventually study the grid using the models that you're which and the math of it you're learning in the school right now. So then the second part is so that is on the generation side. And then on the demand side, there's a lot of change too, right? The whole EV ecosystem, microgrids, virtual power plant, the home residential batteries. They're all on the demand side. And then on the demand side, it's less study based. It's more rule based interconnection. But there is there are studies work not as intense as transmission. But and then so yeah, those are the main change essentially on the generation and distribution side. And then on the transmission and distribution, it's mostly wires, company typically owned by large utilities. Um, there is innovation happening in that domain too, but as you can imagine, anything that is on the wire side obviously takes a lot more regulatory approval, a lot more diligence because of the long life of the infrastructure that you're putting in. So but there is a lot of innovation in that space too. Okay, so yeah, here's a photo of Tesla Megapack on the grid side, just to give a context of what we are doing Tesla as specifically as a company, and then on the residential side, you see a photo of Powerwall on the right side, which is a residential battery. Okay, so I think another thing, which is again, I think something that I learned over time, there's energy system space is humongous. Like I think that's a part I actually like about it a lot. Uh, uh, Now, like especially like it's not like an iPhone. You just build it and sell it to the customer, right? There are many layers behind it that not everyone sees. There is the whole regulatory structure, like at the country level, it's work. Then there are state commissions. There's a lot of standards and compliance, like North American Electric Liability Corporation, and then they have different agencies that polices the compliance, and yeah, so there is all sorts of standards and compliance. There are grid operators that operate the grid on the regional basis, but there are utilities too that operate their own grid called vertically integrated utilities like Southern Company or Arizona Public Service Commission. Um, and then within the utility, there are lot like different financial like or in yeah finance structure like investor owned versus state owned versus co-op, and they all tend to have different flavor of work culture or whatever that comes with it. And then there are developers who are, because now the generation is all um, deregulated, like there's a lot of private players who are building generation, and there's a whole slew of company that came in that domain. And basically they are essentially um, making money by having offtake agreement or power purchase agreement structure, or just making money in the energy market. That's how they recover their cost. And then there's a whole consulting environment, because as I said, all of this needs to be studied. Not everyone wants to maintain an in-house team, like for reasons that you don't want to. And so there's a whole environment for consulting companies. And then it ranges from system studies to the balance of plant study, plant performance, energy market. There is a world of OEMs, companies that are making equipment directly, Tesla, GE, Vestas, like SEL. So they are all the OEM world. of equipment. Maybe we can mute the new person. Seems like there's a background.
Yeah, we just did. Thank you.
Cool. And then there is a software OEM world, which is like Tesla has its own lot of softwares, and like there are companies like AutoGrid, and yeah, and then there's the research environment, national labs, and universities. So I mean, honestly, I believe like if you look at the ecosystem that goes behind energy infrastructure, it's like humongous. It's nothing like anything else you probably imagine. So and that's why it is so different. And to me, that is really interesting. Okay, so I think let's moving on. Energy storage as a concept, like why it is critical. Like so storage is basically critical to absorb any variability, right? And if you think in terms of state variables, storage is your buffer, right? It's a state that you will like to monitor. If you are building a dynamic system, you will put storage as a state variable and just monitor it, right? So surprisingly, and for reasons because technology was not there, storage was not a thing in energy ecosystem. And maybe it was not a thing because petroleum and gas was there in 70s, so people didn't need to like think about storage as much, now as much as we do now. But storage is essential to give you minute to hour to days, balancing for energy. So in a power system, there are really three things if you think about energy, right? That's what you need. That's a thing that you consume over time. It's a time function. Power times power into time is energy, right? So you need to have energy, and then you need to have reactive power, which is the voltage support, right? So the grid really is two things. It's a voltage and a frequency, right? You need a 60 hertz when you plug the charger or anything in your socket, and you need a voltage 120 volts. That's what you want always, right? So meaning the thing that is holding the voltage is reactive power, and you need to balance it out on seconds to millisecond basis. And then you need to balance the frequency too in the grid, and that is your real power, right? So those are kind of your two levers, two things that you really care about: voltage and frequency. And energy is energy, like that is the chunk of, whether it comes from sun or comes from coal, like something has to have energy to provide you that power. um, and then storage as a concept has been there in different industries like air transport, right? Imagine a world where there is no airport, right? How would you like, or airports just have a millisecond, to load unload, something like that, like a data system. Think about a water system. If you don't have storage, how would you get water every time you need it, right? So I think the point being there is a storage in different networks, just not was there in energy. It has come in energy now. And obviously how storage helps is it helps you to optimize the system and reduce the spend on the overbuild, because you have to make sure you have this power all the time. So you'll have to obviously build for the peak demand. So that's where storage helps. Um, and I know there's a lot of discussion about sustainability of the materials, which is I think it's a great thing, because like historically, like how technology advances is people build technology and then you realize, hey, something is wrong with it, and then you course correct it, and then you course correct it. That keeps going on. But I think in case of batteries, um, like material sustainability and recycling has been talked about a lot, because I think like just people, like obviously sustainability is the core concept here with the storage, and people think about sustainability of the battery itself too, so I feel that is factored early on, and I believe that problem. And I think that problem will be solved like as part of the storage problem that industry is solving right now. So I feel it will be less of a problem. Um, Okay, so I think just to get into what exactly Tesla Megapack, the Tesla Megapack is, which is the grid connected storage. So this is like one of the picture of Tesla Megapack next to a wind farm and solar farm, and like like typical megapack plant size, like can easily be like these days 100 megawatt is small, you know. So you're talking about 250 megawatt, 300 megawatt, even 500 megawatt. So the size just keeps going up. And then I think just to appreciate like why is it a difficult problem to solve, you know, like and I think this is generally true for EVs. When I joined Tesla, like I thought like it should be easy problem. It's just a battery and a motor, you know, just anyone can do it. And same for the Megapack, right? I thought when I joined Tesla at the time, I thought like maybe it's an easy problem to solve, but it is a difficult problem to solve for a reason. And like just to show you why, like you see on the like this is a typical structure of a battery storage plant. Like you have a plant controller on the left side. You get a SCADA command from the grid operator, and then you have multiple inverters, as you see in the photo here, multiple mega packs, and they have inverters inside it, battery and inverter both inside those boxes, white boxes. And then even within those boxes, we modularize it even further. And then all of those goes on a different feeder, as I show here, like 3 different feeders, but in reality, there are many, many feeders. And then they all go through LV-MV transformer, then a MV-HV transformer, and then there is a meter at the point of interconnection, which controls this whole plant together. And then there is a grid side interaction of this plant, you know. So I think the core thing here to realize is there is a lot of aggregation happening, which is the magic, right? Here is like how do you keep all these things work together and respond as a plant? It's not an easy thing. There is a lot of software behind it. There's a lot of hardware behind it, right? So and there is a communication network, right? Which is not the case with synchronous machine. There is a measurement device, the meter, right? So point being, I think that like if you want to really simplify this problem and think, you know, why it is a hard problem to solve, like um, then between synchronous machine, a typical natural gas plant versus a typical battery storage plant or any other plant for that matter, like that is modular in nature, be it PV, be it wind, be it battery, or be it other technologies that are going to come in future. Um, maybe modular nuclear, like who knows, like what's coming, like there's a lot of modular technology that are coming. I think that the core thing is there is the add-on complexity of aggregation. There is an add-on complexity of how do you account for any measurement noise or measurement and the delays in communication. So really 3 things, right? Aggregation, measurement issues, and delays in communication. And yeah, so this is really the heart of it. So like so basically about battery storage specifically, um, like as I mentioned, like there are really 3 things you want to, I mean, 2 things from the perspective of real-time control, reactive power and real power. So that those are the 2 core controls. So if somebody gives a real power command to the battery, you have to provide that real power at the POI. So there is some basic control around it. There is some reactive power control. Like if you need reactive power or want to maintain a site voltage or power factor, that control is part of the core control of any plant, battery storage plant. And then you have to like make sure all those aggregated, you know, electrical components are compensated for in the command. So you have to have some kind of compensation in the controls to make sure you meet the command at the POI. And then on top of that, there are other things you might want, other things which is interesting, which is what makes it also different from synchronous machine is like it's a software, right? So you can do whatever you want with the command, so as to say. So you can have different frequency watt, RAMs, operator limits, same for reactive power. And then there is this whole new world of grid forming controls, which in a simple term is nothing but synchronous machine with current limits on it, right? Because inverters can only do so much current, like they are not a mechanical device. So they're very like electronics devices. Switches have their own, MOSFETs have their own limitations. So you have to have some kind of current limits on those devices. So that is really the part of core control here. And then like this is how we kind of show it. Like on the left side is the grid following control, which is like a typical thing that industry was doing. But then all of the industry is now moving, especially in the battery world, grid forming control, essentially behaving like a synchronous machine to provide real and reactive power balancing milliseconds to milliseconds, not seconds to seconds, because you really need to hold the grid every millisecond, right? So you imagine a grid where you have a fault on a grid and voltage goes to zero, and nobody is building the voltage back onto the grid during the fault, like the whole grid is dead, right? So basically you need that control millisecond to millisecond, like so that's why there's a lot of movement to grid forming now. And again, I think another thing I will say here is like grid forming, I hear a lot of research discussion, and again, research has to happen like to make it better and better, but like from our perspective, like it's a problem that solved. Like we most our plants are not grid forming in Australia and like Hawaii especially. So I think moving on, just a common use cases for grid following, as I said, energy shifting, energy markets, power smoothing, meaning if you're connecting behind a wind power plant and wind is fluctuating, then you want to make sure the ramp rates are stabilized so that they don't make the grid unstable. Ancillary service, there is a lot of markets where frequency response is a paid service. So that's another typical application. T&D deferrals, meaning like if you have a line that just get overloaded only once in a year, you probably can defer upgrading that line that till it really gets overloaded, maybe 30 times a year, or something like that. So point being, if there is a super niche corner case of uh, not building a line and you can just supply it with storage, that might just pay itself. So, and again, all these use cases, I don't have that discussion on this slide, but on my other slide, like I also talk about each of these use cases, like has been done. Like every single case that you see here is not a theory. Like all of this has been applied in real life, like with real projects. So same for grid farming. Like load following, like a typical microgrid. Like if you want to plug on any load, like you should just get power, right? So and there is behind the scene there is a machine-like control that is working to always provide you that power. Home backup is basically like you see in a residential battery nowadays. Home backup is nothing but a grid forming control. And I think there's a funny thing I always think about is back in 2020, back in like 2000s, when I was in India in my high school, like we bought a lead acid battery with the inverter for $35, $40. And like I did not realize it's a grid forming battery. So I always like say this in Tesla too, to put in context, like even though it is talked about as a thing that is like oven fresh and never been like done before, like it's been done, it's been there for many years. And like, and this something what we were doing back in India, like in 2000s. Every home had this lead acid battery where you used to refill with rainwater typically, and then it just backs up the home whenever the grid is out, which used to be out a lot. So um and then this whole thing with the grid forming batteries, or the black start on transmission, which is something we recently did for Hawaii Grid. Like at the transmission level, it's available as a service. Like we study it all the time now for different markets. So also like there's this virtual machine mode, which is a little bit different from black grid farming in a sense that when people think about virtual machine mode, I think the mindset is mostly how do you stabilize a plant in a weak grid situation, which is weak grid is nothing but kind of a sense of uh, loose voltage control on the grid, uh, which is when you have maybe a really long transmission line or lack of synchronous machine. Yeah, so I think this is a critical concept. Like I'm assuming, like for your research, especially like if you're researching around inverters based control, like obviously weak grid is a thing that I'm assuming you're studying a lot. Um, and I think maybe one thing for anyone who's studying weak grid for the research. I feel that there's a wrong notion about weak grid, which is all impedance based. And in reality, like it's not about impedance. It's all about like, do you have a control over voltage? Like, for example, you can eliminate all the synchronous machine from the grid. You still have the same resistance in the grid, so same impedance in the grid. Nothing changed on the impedance. The only thing that went away is the voltage control. So point being, like if you have like, yeah, I can do a side discussion on this, like just the important concept to realize. It's people like it's studied as an impedance, even though it's not impedance, it's truly. So I mean, that's why you need, I think, a large scale PSCAD model at some point. So which is where the industry is moving, large scale EMT models. So yeah, I think subcycle inertial response is another thing from VMM, and it can be alternative to synchronous condensers. So okay, I think this is my last slide, like or second last slide actually. Like I think what is power system engineering? I think this is something I try to think about it now. Now I've worked in the industry for some time. Like I feel uh, like to be a good power system engineer, I feel like in today's environment, like to be having an awareness across different courses around power system analysis, machine model of the machines, load flows, optimal flows, power flow, and transmission modeling, stability, like Dr. Mani's class, and like first one is more like Dr. Bose's class, plus maybe some undergrad courses, power system protection, power electronics. I feel like there should be like it should be part of the coursework because you need to know something about the inverter structure. Generally, like even though you might not do this directly as a power system engineer, but it's good to know that architecture. Then power system operations, how does the grid is actually controlled through AGC, EMS, like knowing about basic control systems like Bode plot, PID. This is the one I find most surprising in a sense that I know linear control system like Dr. Sandeep's class was really hard, but at the same time, like in day to day, you're using basic Bode plot, PID a lot. And like, I mean, you would think it's easy to have that intuition, but not really easy. So I think like focusing on that class I feel is very important. Um, like knowing the basic Bode plots and PID controls and having an intuition for it. Then energy markets, how the markets are really structured. Like I feel this is also another area that I'm not sure how many schools have both solid program in like all the electrical analysis and markets at the same time. They are somewhat decoupled, but also there are things that if you go into the nuance of it could be coupled. So I feel like this is if you have handle on both, that's a good thing. Again, but it's non-overlapping subject typically. That's how people think about it, but there could be some optimization there. And then power quality, electric machines. Yeah, I think we talked about this. And in terms of the tools, like learning tools, I feel in the school could be a good thing, like because when we hire, like it just has a ramp to like have somebody learn the tool. And like each tool has its own nuance. Each tool has its own mathematical limitation. So knowing the underlying principles of the tools, um, it sometimes takes time, and it's good maybe if you have chance to study them in the school time too. Like I mentioned, all these tools, PSCAD, ATP, I think it's a free version of EMTP, PSSC, PowerWorld, like RTDS. I know WSU has RTDS already. So some kind of a hardware loop and some kind of a EMT and some kind of a RMS simulation, and having a good intuition of what the limitation of those tools is a good idea. So yeah, and I think the last thing is, I think from the career perspective, I feel, I mean, if you're really excited about energy in general and like the criticality of it, like for the society, I feel like the landscape is huge. You can work in different type of entities, as I previously mentioned, ranging from regulator to all the way being an expert in your domain. Like you can choose to be a stability expert, you can choose to be a prediction expert, or you can choose to be a generalist and kind of know everything. So there's a wide variety of it, or just not just learn engineering, do something in compliance, like who knows, like on the regulatory side. So there's a huge scope to learn and grow. And and I feel like this is one industry that needs people on all sides of the aisle, meaning like you need people who absorb this, not just on the engineering side, but also on the regulatory side. But otherwise, like you can't push things, you can't push policies, you cannot push right designs, and like from the perspective of reliability and cost down. So it's a good thing to have folks coming out from school who join all these different entities, um, and yeah, it's a complex interplay of physics, business, and policy, and it's a it's a long time consuming journey if you really want to enjoy it. Like you have to just wait and watch. That's part of the problem why power system engineers are not as paid as software engineers, because they can build things in 3 month cycle, which we cannot. So just know that limitation. But if you want to do this for a long time career and just like contribute to the energy, I think this real nice space to be in. So yeah, I think I can pause here. So and open to questions.
Yeah, thank you, Prashant. That was very informative talk. So we really appreciate that. So let's go to it seems that my voice is going back.
I think there's an echo, say.
Yeah, that's what I'm saying. I don't know why. Anyhow, so let's go people online. So if you have question, please unmute yourself and ask your question from Prashant. Anybody online? Oh yeah, go ahead. Please go ahead and unmute yourself and ask your question.
So Saeed, I cannot hear you clearly. Can you hear me?
Yeah, we can hear you.
Okay. Yeah. Okay. Nice to see you, Saeed, and nice to see you, Prashant. Very nice presentation. I think this is very interesting work, and I think it's really pioneering work, especially for the grid firming energy storage. I know Tesla deployed a lot of grid firming batteries in Australia and Hawaii. But in the next few years, do you see any trends for the grid firming battery to be connected to the mainland power grid? I see NERC is pushing it very heavily, but from manufacturer's perspective, do you see any opportunities there for them in the U.S. power grid?
Oh yeah, I think there is a ton of opportunity. I think it will come as a push mostly. So like what happened in Australia, the reason it got pushed is because people were just not able to connect at some point because the SCR is too low. So they had to switch to grid forming, I think in US, the reason we can get away with following so far is because we can connect. But I think either it will be enforced by NERC or people will stop seeing, like their studies getting approved without forming. So I think like what would come first, I don't know. But there has to be a trigger, like either external or something, happening in the study process. But I think but at the same time, that is important to know is that will increase studies time, because grid forming, like you have to really study well. Like following is now pretty standard, right? Like there is not much to it other than the PLL dynamics, but forming, obviously you have to study well, so there will be a balance. Yeah.
Yeah, thank you very much. I agree with you. It's we are seeing opportunity there, but it's very complicated things because it's either by the requirements, the NERC recommended that, or the utilities write them in the interconnection requirements, or the market for incentives for grid firming. So it's still not decided yet, but I think this is very important topic. And also from the technology perspective, you are right. I think for grid firming, especially now, the control has not been very well unified. Different manufacturers may have different interpretation of grid forming, so that control blocks, that dynamics will impact the stability differently because of their controls. But recently I heard that at Hawaii Island, they require 1.6 per unit of the contract capacity for overcurrent for the plant for 5 seconds. So I'm wondering why they have that kind of requirement. Is that caused by the stability or caused by the voltage support, or do you have any insights for that?
Yeah, so I think it's a new requirement. I think generally, I mean, at the fundamental level, if you think about it, is like if everything is inverter based, you would need enough current to run the protection, right?
Yes.
And then I think 2 per unit is sufficient to distinguish 1 per unit versus 2 per unit. That is our assessment. So I think eventually it would be close to 2 per unit. And like what would bring it first, like whether a requirement or a like a policy push or a project need, like depends, but has to be somewhere there, you know.
Yeah, I also like 2 per unit. I think that's better for grid
Yeah.
firming control design and also for stability. As you mentioned, grid firming is a synchronous machine with current limiter. But if you really start to limit your current, you have very limited capability to regulate your voltage within the current limit, and also that might cause stability concerns. That's based on my understanding. If the overcurrent capability is very low, but I think the reason is the cost, right? If you have 2 per unit overcurrent, how much does that increase the cost of inverter? Maybe not. I don't know.
No, not
Not
a
too
whole
much.
lot. No,
Not a
yeah.
whole lot.
I mean,
Because
inverter anyways is a very small cost of the whole battery storage system, right? Mostly it's battery, right? So not a whole lot. Yeah.
Yeah, thank you very much for the information, because I think you're requiring even 2 per unit is just for short term, for a few seconds. I guess that's enough.
Yeah,
Maybe for 2
exactly.
seconds. Right?
Exactly. You can do a lot of other things. Yeah. So I mean, it's not a burden. Yeah.
Okay. Thank you so much, Prashant.
Yeah.
Thank you.
Yeah. Thank you.
Thank you, Wei, for your good question. So, any other people online have questions you want to ask? No? Okay, so people in the room, so please go ahead and ask your question.
Hey, thank you for your presentation. You talked about for tools that students could use to learn before we go into the field. You had a whole bunch of simulation softwares. As students, we won't necessarily have time or access to all of these, but if you were to grab one or two to recommend to us, which ones would you suggest?
Yeah, I think try ATP. ATP is free. PSSC, and I think PSSC was there at least at the time I was in the lab. And then on the so ATP is basically EMT simulation. PSSC is the RMS world, and then RTDS is already there. So I think if you pick 3, ATP, PSSC, RTDS, that should be sufficient.
Okay, yeah, thank you. And I have another simple question. So Tesla's developing those mega packs. What's the typical services that those provide? Are they just acting as a buffer between PV or renewables and the grid, or are they providing other services primarily?
Yeah, basically all the services we talked about. So there's a lot of power systems control that is in there. So basically it's energy, real reactive power, and grid forming controls. So all of those capabilities are there.
Yeah. I was just wondering because in a previous seminar, someone said that the ideal load is constant all the time. And it made me realize that if the grid could have a more consistent load, then the need for inertia goes down pretty significantly if we're able to regulate the flatness of that load. And so I was wondering if that would be a good application for a megapack being a substantial power provider as an ancillary service. So basically, if you flatten the load, you don't need nearly as strong inertial response, synthetic inertial response from inverters.
Yeah, no, I think precisely this is, you can maybe search online. There is a project called Cooley project that is coming in Western Australia. So Western Australia has so much solar in the daytime, like it's almost the duck curve thing that you see, starting to be almost, zero. So that's why they're putting the huge battery there to kind of absorb the belly. So and also have the inertia during that time. So they cannot turn off all the machines just because everything is coming from residential. So yeah. But also this is a very interesting topic. I personally feel is like how much of it will be on the residential side, how much of it would be on the transmission side, and would both side built up too much for making it too expensive. So like it's a pretty interesting thing that will evolve. I'm pretty curious to know what will happen.
Yeah.
So
Well, thank you.
I have a question. So actually, I have a comment and a question. So my first comment is, you mentioned that in India that you actually got used to the grid following inverters before the grid following, which is also true for someone like me, because I'm always surprised when I hear that, oh, the grid forming inverter is a new technology, because I've actually known I've known the grid forming inverter for some years, even before I heard of the grid following inverter. So it always comes as a surprise to me to think the grid forming inverter is actually a new technology, because I've always considered the grid following to be the newer technology.
yeah.
So yeah, it was good that you actually touched on that. So I think it depends on maybe where you're from, right? Because in my country too, we even before the advent of before the popularity of renewable energy, we were actually using lead acid batteries with 500 watt grid forming inverters, and it worked. So, but my main question is, looking at the system that we have right now, like the generators, the conventional synchronous generators. One of the major benefits is the fact that they have inertias, right? Like even though the load is changing at a faster rate than the response of the generator, but the inertia of the rotor helps to balance the power flow, right? But now that the whole system is turning into IBR technology, do you think even wiping out all the conventional generators and replacing everything with IBR, do you think the advantage of the IBR, which is the fact that it is faster, right? It responds faster to load changes. Will that be enough to serve? And also the battery backup that we're talking about, installing a lot of backups, which essentially serves as the inertia for the system. Do you think that would be enough to replace or to stand as the inertia for the conventional synchronous generator if we were to like wipe out all the synchronous generators in the system? I mean, I feel it should be, right, but it's something that
Yeah, it should be basically. I think that's the answer. It should be like there is no. I mean, as long as you have enough current, like the 2 per unit or whatever that limitation is, you should be. I mean, fundamentally, there is no difference. I mean, you have a programmable inertia, even, so you can program whatever you want. So I don't think there will be a limitation. It's only a matter of time, an application where we already see that in microgrid, and like same thing applies. I actually wonder, what people did in those inverters in our time. Did they model the machine? Someone must have done that, right? So that's how probably they survived. But there has to be something too in those small inverters that we have back in India, like because you are turning on lights and loads, and they're just picking it up right away. So there has to be something about it. So point being, I don't think there is any fundamental limitation here.
all right, thank you.
Yeah, and I think too, one more thing is when I said that first time that comment in Tesla, took me a lot of courage to say it, so I had to think 3 times. Just make sure I say it in a way people don't feel unhappy about. So
Any other question from people in the room? Or one question also related to, so You know that when you have group control in inverter, basically as soon as at some point if you need extra power to inject the grid, it should be available. So then we put the energy storage inverter.
You're not coming through, Said. I think it's breaking a lot.
How about
Breaking a
that?
lot.
Dr. Said, I think your network is not so great. We can't hear you clearly at all.
So we just.
Someone.
I think we have questions in the chat that we could hear.
Is there a question in the chat?
I think two of them.
Yeah, can you guys see the questions in chat and have those been addressed yet?
There's no question.
I'm sorry, the raising hands in the
I can
lobby.
check.
Yeah.
Yeah, there's a couple questions in chat. I don't know if you've addressed them yet. Thank you.
Yeah, I can do that. So yeah, I think there is a question on V2G and VPP. Yeah. So V2G, I think is an upcoming thing. I feel not many people have done it. Like I know Ford has done it. I mean, I'll just say what like typically Elon says, right? I mean, it's like, do you need to use the vehicle battery necessarily for grid, or you can just have a separate power wall? I mean, it's not rocket science, right? At the end of the day, I think where everything is going is generally people will have a DC bus in their house, right? Where you connect a PV, a car, or and then have a common inverter for everything. So point being, yeah. So I mean, it could come. There is no reason why it should not come. And the only thing is, does it make a financial sense to have to use the vehicle car battery, or does it you just have a separate battery in your house? So yeah, so VPP and the VPP side, the VPP initiative, I also think that is a thing that I feel like in the industry people think it's far out, but like Tesla has done VPP in Texas, in Australia, like 50,000 plus homes. So it's there already. And like there's a Tesla electric plan actually in Texas now, where we use VPP to kind of pay back to that plan. So we are kind of the electric utility there. So yeah, so that is already there. We are expanding it quite a bit. You can read about Green Mountain Power. That's what they're doing. We are doing it in California too, in Australia. So yeah, it is a thing already. I think there is a question about Tesla plan to transform aggregated power wall as grid forming VPP. Yeah, it's already happening, as I said. What are the challenges in transforming Tesla grid following units into? Yeah, so it's just a software change today. Yeah, I get that question a lot. So no. Other than that, you have to study. So it's mostly on the study side. You have to study following to forming change, but nothing much on the software side. Yeah.
Hey, thank you. I changed my internet network, so hopefully this time is working. Is it better or?
Yeah,
Okay.
much better. Much
Okay.
better.
I know I go on my cell phone network. Okay, that's better. So yeah, a real quick question. I was saying that, so when, for example, when we have a group control on inverter, so basically we assume that we have energy storages. But I hear some people also saying that we can derate the operation of the power grid, basically underutilize the, for example, PV farm, don't operate at the maximum power point tracking. So go a little bit below that one such that you have available such a thing. So is it something that done in this way in the industry or not? This is more on papers or?
Yeah, I think people can do it. It's just a human thing, right? I mean, if you have a surety of making money, right, you would make it now, right? Why would you wait for a great event, right? So you'll always dispatch the maximum. So yeah, I think that's what it comes down to. So I think some things are doable, but like what you end up doing, and how do you manage that? Like who monitors, how much you have to dispatch, becomes a thing. But again, these are solvable problems. There is a need, it's like, so, yeah.
But right now, for example, in you said that you implemented some PV farm in the Hawaii. So over there, that was totally based on the battery energy storages?
No. So we had a battery storage farm in Hawaii.
Okay.
That is just completing, fully good farming capability. Yeah.
Okay, sure. So therefore, right now it's mostly reliant on the energy storages. Yeah.
Mostly, yes, yeah.
Yeah.
But we can totally do grid farming too. I mean, there is no reason why not. So.
Okay, and also about the resource, the services. What is your comment? And for example, right now, most of the services we expect from the plants and even inverter-based plants, basically based on the conventional synchronous generator-based system. For example, you have frequency response, voltage control, and so on and so forth. So do you see that what are other services maybe we need if we go to the inverter-based power plant? So have you faced such a problems yet or not? You think that it's more on the futuristic kind of thinking?
Yeah, I think I don't think there is, like, from the service perspective, there is a gap right now. I think anything that needs a service has been talked about in the industry, which are these basic controls and then machine like control. But I think maybe where things can evolve is, can you, like, how do you reduce the burden of studies? I think that could be one thing, that can evolve, because these things are now settable, they are software controlled. So can we do something about it? Meaning, can you just, have a self-tuning plant? I think that is a long shot discussion, but maybe industry will move in that direction. So yeah.
Okay, thank you. Yeah, thank you.
Yeah. Yeah, thank you so much. And yeah, thanks for having
me.
me.
Any other questions? Maybe if anybody has, if not, no. Okay, so if not, let's thank the person for his very interesting and informative talk. So let me give a round of applause to him.
Yeah.
Okay, thanks a lot, and hopefully see you sometime soon.
Yeah, thank you. Thanks. Yeah, bye.
Okay, thank you. Bye.